Welcome back to our session on inferring effective network structure using the transfer entropy. In the previous short video, I gave you a first look at the iterative or greedy approach using multivariate transfer entropy for network inference. In this next short video, what I want to do is flesh out some of the subtleties around that and show you some more detail and steps there as well. Okay, so up the top here in this box, I'm showing you the algorithm that we were left with from the previous slide. This simple first pass look at the greedy approach. Let's look at some of this in a bit more detail. Firstly, we need to understand there's a 0th step here, which is to embed the target past. Okay, we need to do that first, and we need to do it properly to avoid false positives, as I previously referred to some of Vibral and company's work in showing the importance of doing that. Then what we need to understand here is that this approach, this greedy approach where we take one regression route to flesh out who the set of parents are in our effective network, is more efficient than a brute force search for the parent set. As I said, we need to keep our key goal in mind is to infer that set. It's kind of getting to this collective transfer from that set of sources to the target. But if we just search for the set of sources itself, that can be very combinatorially difficult. So taking a greedy approach where we build our parent set iteratively is much more efficient. It also handles redundancies and synergies between the parents for us. By gradually conditioning on the parents that we've already selected, we make sure that we don't select sources that only have redundancies with those ones. And we can also pick up synergies between our new candidates and the sources that we've already selected as parents. So that's very good. It addresses those big concerns we had about using the pairwise transfer entropy alone. There is still some potential for things to be missed. For example, here, if Y and Z have a solely synergistic outcome on X, if we can't see any pairwise information from either of them on X, then we won't pick up one in a first pass looking at the pairwise alone, which won't even let us get to that next stage of picking up the synergies from the other one. Okay, that's potentially a problem. Now, we could address that by looking at pairs to start with, which is very involved algorithmically, so we're probably not often going to do that unless it's a smaller network. But we also need to bear in mind that it's kind of rare to get a purely synergistic interaction. Even with an exclusive OR relationship from Y to Z on X, there's usually going to be some kind of symmetry breaking in the network that ensures that we will see the signature of at least the effect of one of Y or Z on X to start with, that makes picking up the second one a lot more easy. What we could also do here is to scan for multiple samples from each source. In everything we've looked at, we've just considered looking at the previous time step. That's what we can see in our mathematics here. We're just looking at time step n for our sources to target n+1. We could scan across multiple time lags, and we can select multiple samples from each source as well in a non-uniform embedding that I'll show you in more detail later in this short video. We need to understand also that our statistical tests here at step 3 provide an automatic break for us when the statistical power of the data is exhausted. So if we don't have many time series samples, we may not be able to reliably infer the whole set of parents for X. Our statistical tests will make sure that we don't overstep that mark. They'll make sure that we can only infer as much as we have power for in the data that we have. And that's really nice. It's coming back to that idea that we first had when we looked at the basic approach of thresholding the transfer entropy. Our threshold now becomes adaptive to the amount of data that we have, which is a really good thing. We can also think about adding additional tests to our algorithm as well. Here, steps 5 and 6 we didn't consider before. We can add some final steps here. We can look at pruning redundant links in our final set of parents. So we may find that we inferred one source early on, but once we've gathered our full set, maybe the information provided by that source is fully redundant with some of the other parents. So we can do a pruning test to see if there's anything we could remove to have our minimal circuit model. we can then perform statistical tests on the whole parent set that we've inferred here. That can be a way of helping us to control for multiple comparisons. And that's something we do in the IDTxl toolkit that I'll talk about in the next few slides. Specifically, what we do there is when we perform our test of statistical significance, we use something called max statistics. So instead of just taking the p-value of our conditional transfer entropy against surrogates, what we do is we take our surrogates across all the candidates that we examine. We take the maximum for each surrogate index across our whole set of candidates, and we get what the statistics would be if we picked, if our maximums were coming from only the surrogates alone. Okay, this gives us an alternative way of constructing our statistical tests that can be more appropriate than using the Bonferroni correction. It's certainly less harsh and it still retains meaning. More details on that are provided by Volstadt et al. Regarding the IDTxl toolkit. Importantly, the end result is our parent set here. The order that the nodes were inferred in when we did our regression, when we did our greedy search, is no longer relevant. Once we've finished the algorithm, all that matters is who the set of parents are. Okay, and that's reflected in our final statistical test of the whole parent set. This also aligns with statements we made in the information transfer lecture, where, in considering the joint transfer entropy from a set of sources to a target, we said that this joint transfer was the whole model, and we view the various ways of extracting subcomponents of that whole via pairwise and conditional transfer entropies as submodels. Let's have a look one more time at the algorithm, and this time let's just focus on a representation of the system. So here we've got our multivariate time series. We've got our columns of variables. We're going to think about x as our target, and in particular we're looking at where we take the information from to model how that value of x at time step n+1 is being processed. What we can do here is have a time horizon that we're looking for those information contributors within. So we're not going back beyond the length of that time horizon. Our first step here is to embed the target past. So here we look at candidates up to the end of that time horizon. That's our maximum embedding length. What we do then is in selecting our target variables, we do this in a very similar way to what we do for the sources here. So we're going to look at a non-uniform embedding, and we're going to select target candidates based on the information they provide about our target next value, conditioned on who we've already chosen. So we can see then an iterative choice, an iterative selection of those target past values. Once we've done that, we can then think about selecting sources now. So we can evaluate the transfer entropy from every candidate source, all of our variables, all of the possible time lags, to the target, conditioning on the parent set that we have already. And here we don't have any parents selected yet, so we just do pairwise transfer entropies first up. Once we've done that, we add the source with the maximal conditional transfer entropy to our parent set if its p-value from our max statistics was statistically significant. We can then go around again and select the next source to add if its p-value is statistically significant. And again, picking up another source, and again for another, until we get to the point where no significant sources were found. And then we go and we perform our final statistical tests. Okay. So that's a view on how this expanded greedy approach works. You could think about trying to expand what we've done with JIDT in some of the previous short videos in this session. You could think about expanding that code to implement this algorithm as a whole. And you can do that. However, there are a lot of subtleties here. So instead of you doing that yourself, what I would recommend is that you look at our other toolkit, IDTxl, which is a higher layer toolkit than JIDT. It uses JIDT as an internal information theoretic engine under the hood to perform the information theoretic calculations, and it has the higher layer algorithms around that to implement the greedy algorithm, including some of the steps I've just gone through. The maximum statistics for multiple comparison correction. It handles the parameter selection for transfer entropy, the non-uniform embedding, and the delayed selection of sources, and it adds these additional steps, including the pruning step that we've just been talking through. So if you have some time series data that you want to do effective network inference on, I suggest you look at IDTxl as a more holistic package for that purpose than JIDT. So here in this session, we've looked at different options for network inference from time series data. We looked at structural network inference, we looked at functional network inference, and we settled on effective network inference as the approach that was kind of most closely aligned to our view in modeling the information processing in complex systems. We also looked at the complexities and subtleties involved in effective network inference here. We talked through some of these simple pairwise transfer entropy algorithms for effective network inference and how to do that with JIDT. We also talked about understanding the advantages of more advanced techniques that lie in the IDTxl toolkit using the greedy algorithm. So that just about brings us to the end of our course on using information theory to analyze complex systems. Coming up next in our final session, I'm going to summarize what we've looked at so far and what we've learned.